Greetings, fellow humans. Welcome to Chapter 7. This is going to be a big one. We're looking at all kinds of new stuff. We're going to be fading an LED, first using code and then using the knob on a variable resistor. We're going to learn how to debug our code by sending messages to the serial monitor. We're going to use push buttons. We're going to use wires. We're going to learn how to design our circuit diagrams. It's going to be great. So saddle up, let's get started. The first sketch in this chapter is the LED fade sketch. We're going to fade an LED, more or less the same as a dimmer switch. And we're going to do that with pulse width modulation. And the Uno has several pins that are designed to do pulse width modulation. For this sketch, we're going to need 2 jump wires, the breadboard, the Uno, 1 LED, and we need a fixed resistor that is 120 ohms or greater. I don't have one that's exactly 120, so I'm going to use one that's 220. Before starting into the LED fade sketch, the Dummies book talks briefly about pulse width modulation, or PWM. PWM is essentially when a digital device simulates an analog power source. I recommend going to the sparkfun.com website to read up on PWM and duty cycle. Both of them are relevant to this sketch and other things that are coming up later in the book. I found this Uno diagram template on the Arduino website, and I think this will be just fine for most of the sketches we do in the Dummies book. So I have crudely sketched out the diagram for the LED fade sketch. And it's quite simple. We start from our power source on pin D9. It's a PWM pin. It goes to the LED first. Then we have a 220 ohm fixed resistor, and then it comes back to ground. So if you're wondering why we need a 120 ohm or greater resistor, I was wondering the same thing. And the Dummies book does explain this. And we're going to use some information that we know about the Arduino, plus some information that the author of the book knows about the LEDs that we use, and Ohm's law. So here's what we know. Our voltage at the source is 5.0 volts, as it is on most of the pins on the Arduino board. The LED, the book tells us that it consumes 2.1 volts, and it draws 25 milliamps of current. So by knowing this, we can use one form of the Ohm's law to calculate the resistance that we need to put in the circuit. So here's what the book tells us. So Ohm's law tells us that resistance equals voltage divided by current. In this case, the voltage is going to be the voltage at the source minus the load. At least I think that's what the VL means in the book. So we're going to have 5.0 minus 2.1 divided by I. Now our current needs to be in amps, not milliamps, so it's going to be 0.025. I'll use a calculator for this one. So 2.9 divided by 0.025 equals 116 ohms of resistance. So what the book tells us is that if we have 116 ohms of resistance, then the circuit will be perfectly balanced. Now, it also says that in most kits, you won't find that exact type of resistor. The next one up that you're likely to have is 120. Unfortunately, I don't have one of those, but I do have 220. And the book goes on to say that it's okay to have more resistance than the ideal amount. And it says suitable values from various kits would probably include 220 ohm, 330 ohm, and 560. So I have 220, that's what I'm going to use. So I've done my best representation of the sketch on page 95. So I'm using one of the PWM pins. That's pin number 9. That's my power source. So we should get 5 volts coming out of this one. It goes into the long leg of the LED, goes through it, lights it up, comes out the short leg. From the short leg of the LED, it will go into the fixed resistor, through the resistor and out here. Then after it exits the resistor, it will go to the black wire, and the black wire goes to one of the ground pins on the Uno. So the last thing I need to do is get the software for the fade sketch, and I'll probably tweak it a little bit from the example, and then I'll upload it to the Uno and see what happens. I've got the Uno all wired up and powered, and I've got my fade sketch ready to go. So I will compile it and upload it. And when I press upload, I really hope I see a fading and unfading LED. Yes, there we go, in all of its glory. All right, it's a little underwhelming, but progress. All right, I'm gonna go turn down the lights so that we can see this beautiful glowing LED a little bit better. Glorious. Let's take a little closer look at the code while the beautiful LED continues to fade and unfade. I don't know if unfade is a word. I'm going to make it a word for now. All right, so pin number 9, that is the pulse width modulation pin that's providing the power. I declared some constants to make the code just a little bit easier to read. So a pulse width modulation pin has values between 0 and 255. So I wanted to declare these to make it clearer what's going on down here in the code. The delay we're using is 20 milliseconds. So every 20 milliseconds it will adjust the amount of voltage either up or down depending on whether the fade is increasing or decreasing. Fade amount is how much it's going to change each time through the cycle. The brightness is just the current brightness of it. We start at 0. This is changing so fast that doesn't really matter. So each time through, it's either going to add 3 to the brightness until it gets all the way to the top. Once it gets to 255, it will start taking away value, it'll take 3 away until it gets all the way back down to 0, and then it'll just keep starting over again. So in this sketch, we're using analog write. So if you remember back to chapter 4, when we were just turning an LED on and turning it off, we were using digital write. So digital write will only use binary values, so either on or off. Analog write is using the pulse width modulation, so it takes a value here of, oops, this environment's a little twitchy. It will take values between 0 and 255. Right here is where we're making the adjustment to the brightness every time through the loop. And here is a statement where it says if we're at the minimum value or the maximum value, then flip the direction. So if we've come all the way down, we'll start going back up. If we've got all the way to the maximum, we'll start going back down. And here's where we set our delay. So nothing too complicated here. The next sketch is the button sketch. For this one, we're going to use the Uno, a breadboard, a 10,000 ohm resistor, a push button, an LED, and 3 jump wires. I'm going to zoom in a little bit on the button, as this is the first time we're going to use one. The things are really tiny. This one's in the breadboard right now. I'm just going to pop it out. Take a look at the size of that. Very small. But they fit perfectly in these breadboards, and it fits across that gap in the center. And when you push it, you can tell when you've pushed it. There's a nice little click sound, so you don't have to guess. Here's my crudely drawn representation of the button sketch. So we start from a 5-volt source pin. It travels to the push button. After the push button, there's 2 directions here. It can go to pin number 2, which is going to be set to input mode in the code, which we haven't seen yet. Or it can continue down this way to the 10,000 ohm resistor, and then after that it will return to ground. So this is the first time we're using an input pin, and I'm not quite sure how that works. What I don't understand is, does any of the current flow through this pin and through the Uno and go somehow back to ground? Or is this just listening? Maybe listening is not the right word, but is it detecting the current that's passing through the other branch of the circuit? And I don't know. What the book does say is this setup is used to compare ground to a voltage so that you can tell whether the switch is open or closed. So that leads me to believe that this is just detecting what's going on in the rest of the circuit and that it's not flowing through, but not 100% clear. I may have to do a little extra reading to understand that part. But for now, let's just follow the sketch as it's given in the book and see what happens. I've got everything wired up now. So I have the red wire plugged into one of the 5-volt pins on the Uno. So the current should flow this way. Then this wire is connected to the same row as the button. If the button is pressed, it'll allow the circuit to connect to these 2. So on one end we've got a fixed resistor, and we've also got one side of the signal pin. So the signal wire. So that wire will go over here to pin number 2, which is going to be in input mode. Then the current will flow through the resistor
to the other end, which is connected to a black wire, and the black wire just goes to a ground pin on the Uno. The stuff over here, it doesn't really matter as far as the wiring that we've done is concerned. If you think back to chapter 4 where we did the simple lighting up an LED sketch, we've got this LED plugged into pin number 13 on one end, and then on the short leg is plugged into ground. This stuff is controlled internally by the Uno board, so it has its own internal resistor, and we really can't screw that up. So as far as we're concerned, forget about that part. It's not relevant to all the wiring we're doing over here. This is turned on and off by the software, which we'll open up for our sketch, but we don't have to worry about the resistance or voltage over here. That's sort of taken care of internally. So I've got the Uno plugged in, everything's wired up, and I've taken the liberty of already uploading the software. So here comes the moment of truth. Will the button light up? Will it light up the LED? And it does. Yay! Alright, it's a little underwhelming, but that's what it's supposed to do. So if you'll notice in here, it's lighting up the big LED, but it's also lighting up the little amber one that's built into the board. It's supposed to do that. That little amber one is wired into the same internal circuit that pin 13 is wired into, and that's where this big guy is plugged in. So that's all it does, really. Let's take a quick look at the code. So I've declared a couple constants up here, and this is just a very slightly tweaked version of the sketch that comes with the Arduino IDE. So you would go File, Examples. This one's under Digital. Yeah, Digital button. I'm not going to click that because I don't want it to undo the changes I've made. So button pin is number 2, and that refers to the pin where we have the signal wire plugged in. LED pin 13, and like I was just saying, that is the pin where this guy is, and it also refers to the little amber built-in one that's on the board. Button state will either be high or low, which I think probably translates to 0 or 1. It's digital, so it's only going to have one of those two values. So in the setup, we're setting up the LED pin to output mode. We've done that before. This is what's new. We're setting pin number 2, which is where the yellow cable goes, to input mode. And it should get a particular signal if the circuit's complete and a different signal if it's not complete. So down here in loop, as you remember from previous sketches, as soon as the Arduino is initialized, it will keep running this loop method over and over and over forever. So every time it goes through, it's going to do a digital read on pin number 2, and it will only get a value of either high or low. And, you know, let's fix this right now. That's annoying to me that it's 0 up here but high or low everywhere else. Let's set this to, actually let's set that to low. There. That makes more sense to me. Okay. And it's still working. So what we say here, it's going to be constantly going through this loop and constantly reading that pin number 2. And on each cycle through it will say if the button state is high, turn on the LED. If it's not, turn off the LED. Now to us it looks like nothing's happening here, but this loop is running at a crazy speed, constantly checking to see if it should update the state of the LED. On, off, on, off. That's all there is to it. One question I do have is, why do we need a 10,000 ohm resistor in the circuit? I can understand that we would want to have some resistance in the circuit, but why 10,000 in particular? That's what I use because that's what the book says to use, but it doesn't really explain why that value. Why not 100? Why not 100,000? I have no idea. Hopefully some of these things will become clearer as we do more sketches further on in the book. Next we'll be doing the analog input sketch. For this one we need the Uno, a breadboard, one LED, 3 jump wires, and a variable resistor. You can see on the top of this variable resistor that it's marked 10K. That's the maximum resistance this one can support. It should go from 0 to the value that's marked on the resistor. Here is my crudely drawn diagram of the analog input sketch. So as usual, we start with a 5-volt input. It travels along until it gets to our variable resistor. Then it continues the rest of the way till it gets back to ground. We're using for the first time one of the analog input pins. And I guess this is the symbol that we use to indicate a variable resistor. It's a little diagonal arrow drawn through the squiggle line. Sorry if those aren't the right technical terms. As you know, I'm new at this. So if you remember in the last sketch when we did the button input, it was wired to pin number 2, which is a digital pin. So it could only read 2 values, on, off, high, low, however you want to put it. Apparently the analog input pins are able to read a range of input values. So that's going to come in handy when we turn the knob on the variable resistor, and it should be able to give us a reading of the relative position between the lowest and highest value of our resistor. So we should see how that works when we get to the code. Okay, I got everything wired up. This one's pretty simple. The hardest part for me was pushing that variable resistor into the breadboard. It resisted going in, and I had to give it a good shove to get all 3 pins to go into the breadboard. The pins lined up, but for whatever reason, maybe the pins on the bottom of the resistor are bigger than the jump wires, but I had to give it a good shove to get it seated. But it's all good now. So you'll want to have your source, your power source wire on one end, your ground wire at the opposite end, in the middle signal wire. So if we trace that back to the Uno board, the red wire goes to a 5-volt pin, the black one goes to one of the ground pins, and that yellow signal wire is going to analog in pin 0, and it's, let me zoom in on the board, it's the one marked A0. And when we take a look at the code, this should all make sense.
Alright, fun times. I've had my first real failure. So I plugged in the USB to the Uno, tried to upload some code, and the USB froze. It also took out a whole bunch of USB devices on my primary PC. Now, I got lucky. I rebooted the primary PC a few times, and eventually all of the USB devices came back, as you can see in the screenshot. Initially, a whole bunch of those had a yellow warning triangle on them saying that the device could not be read. That really freaked me out. I thought I had done permanent damage. Apparently not. So I don't want to take that risk again. I can't afford to wreck my primary PC. So I'm going to isolate it from directly connecting to the Uno. I've got an old laptop that I've cleaned up and got it working again, and I've installed Chrome Remote Desktop on it. So what I'm going to do is install the Uno IDE on the laptop. I'm going to remote into it from my primary PC. The laptop's just going to sit in a corner on a different desk. But I've got a long USB cable that can reach to it, and I'll have the Uno on my desktop. I'll plug into it and just issue the commands through the remote desktop. So I think that should do a good job of isolating my primary PC from any damage from a bad Uno or me wiring up a build incorrectly or whatever. I don't want to destroy the old laptop, but if it dies, I'm probably not going to cry about it.
So I have already uploaded the code to the Uno and everything seems to work. I'll plug it in now. Oops. So I'm going to turn the variable resistor all the way to the left. So this should be the maximum amount, or it'll be the maximum value that it will send across. And for some reason I've got a loose connection in my big LED. There. So if you look at the code, you can see that what it's doing, we are reading on each time through the loop, it's reading from that analog 0 pin and getting the sensor value. And what the book says is that the analog pins will read a value between 0 and 1023. So right now I'm guessing it's getting a value around 1023 if my variable resistor is working correctly. So the next thing it does is uses digital write to turn the LED on pin 13. Then it does a delay based on what it read from the analog pin. And then it turns the LED off. And then it delays it for the same amount that it got from the analog pin. So if this is reading the maximum value of 1023, then it will turn the LED on, wait for 1.023 seconds, turn it off, wait for another 1.023 seconds, and then continue over and over again. So what I'll do now is turn the little knob on the variable resistor, turning it to the right. That should make the value smaller, and we should see the blinking become faster because those delays are going to get shorter and shorter. I'm going to keep turning it, keep turning it, keep turning it, and the blinking will just get shorter and shorter. So this one's not particularly exciting. If I turn this all the way, the blinking is going to get so short that we're going to get that weird effect where it almost seems like it's just on, but it's blinking faster than we can see it. The funny thing is, when I turn this all the way to the right, the big LED looks like it's just on, but the little amber LED that's built into the Arduino doesn't appear to be on at all. Not sure why that is. I'm going to turn it back to the left just a little bit. There, now I can see the amber one come on. So that's all there is to see for this sketch. One of the sketches that's coming up later in this chapter will allow us to use the Arduino development tool to see the values that are coming through on this, and I think that's going to be a lot more useful than the blinking. So let's cut this one off and move on to the next one. Next up is the DigitalReadSerial Sketch. This is one of the examples that comes with the development environment. You find it under Examples, Basics, DigitalReadSerial. I'm not a huge fan of theirs. I've tweaked it a little bit to make my own. In their example, it doesn't use the LED, but I like to have that. So the point of this sketch, well, first let's look at the setup. Setup is identical to the button sketch that we did earlier in this chapter. So we've got 5-volt power supply coming over here. It's connected to a push button. If you push the button, it will close the circuit, and then we will get our flow going over to both the signal wire that's connected to D2, as well as the 10,000 volt resistor, and then the black wire goes back to ground. So nothing new there. The only change is what's in the source code. So let's take a look at that right now. So up here we declare the input pins so we can tell if the button's been pushed or not. The LED pin, which I use in my example, but they don't use in theirs. In the setup, this is a big change. We're setting up serial communication, and that will allow us to send text back through the USB cable to the PC, and the development kit will get that text and display it on the screen. So that's a great debugging tool. Let's quickly look through the code before I open up the serial monitor. So we're just setting the pin number 2 to read the state of the button. It'll either be high or low, 1 or 0, whatever you want to call it. And we're setting the LED pin 13 to our output pin. So what I'm doing down here in the loop is each time through the loop, it will do a read on pin number 2 to see if the button's pressed. I declared a variable up here that lives outside of the loop and records what the button state was the last time the loop method ran. So then down here I say, if the current state of the button is different from what it was last time, then we'll do something. And the something is, it will check to see if the button's pressed. If it is, it will send a message on the serial port saying the button is pressed, and it will turn the LED on. If the state is changed and it's currently not pressed, then it will turn the LED off and send the message the button is released. And then after we exit this if statement, we have to save the current button state to our variable here. Otherwise, and this is getting into a little bit of coding stuff, because this variable is declared up here, it will exist for the whole life of the run. But any variables you declare inside here, as soon as the loop finishes, those vanish forever. So what we're doing here is taking current button state, setting it in our variable that's going to last for the whole run of the application. And then the last thing we do in loop is set a delay. The book says if you don't set a delay and it runs too fast, you can overwhelm the serial port. So we'll just follow that advice. And a delay of 1 millisecond is the smallest we can supply to it. So let's plug in, see what happens. Okay. Oh, I usually like to upload the old blank sketch from chapter 4 when I'm done running a sketch. That's sort of like a test pattern for me, and it's the one where it will just blink for a second, turn off for a second. So that's what is running right now. So let's upload our DigitalReadSerial. These uploads, well, not the upload, but the compiling part is a lot slower on the laptop, but still only takes a couple seconds. So press a button, we should see the LED come on, off, on, off. Okay, nothing special there. You might notice every time I press it, we'll see the little transmit thing light up. See that? That's because it's hitting that serial print line statement. So in order to see that, we have to go to Tools, Serial Monitor, and open that up. And you notice the serial monitor is set to 9600 baud, and that is the same value that we set here in the setup method. So let's see what happens now when we press the button. Button is pressed. Button is released. Pressed, released. You can click that as fast as you want. You're not going to overwhelm it. And that's it. So now we have a nice debugging tool to get information from the Arduino about what our code is doing. And we're going to expand on that in the next sketch. I have the next sketch all wired up, and this one's called AnaloginOutSerial. This is another one of the examples that's built into the Arduino development kit, and I've got everything wired up. So for this one you need 2 sets of red and black wires. I mean, the color doesn't matter, but it makes it easier. And you're also going to need 1 signal wire, so that's 5 in total. You're going to need an LED, a resistor that's 120 ohms or greater. I'm using 220. And you're going to need your 10K variable resistor. So this one's kind of a mashup of some of the earlier sketches from this chapter. This is putting together the fade sketch and the sketch where we're using the variable resistor and taking a reading off the A0 pin. So in this one we've got 2 circuits really. Coming off of the 5 volt, we go to the variable resistor, and like before it's connected to the A0 pin, and then that continues to ground. So we're going to be using A0 to read the position where we've turned the knob on the variable resistor. And if you remember from the earlier sketches, that will always give us a value somewhere between 1 and 1023. Now on the other side, we're going to use one of the pulse wave modulation pins. We're going to use D9 like we did last time. Which one was that? I don't even remember what the name of that sketch was, but we're going to use pin 9 for PWM as the power source. That one goes to the LED. In that circuit, we're going to have a 120 ohm or greater resistor, and like I said, I'm using a 220 because I don't have a 120 in my kit. And then that one goes to ground. So if we take a look over here, here's pin number 9. So that's one of our power sources. That is going to go through the LED. I'll pop that out so you can see. The long leg goes in the same row as the power cable, and then the short leg comes out on the same row as one end of the resistor. So then the flow will go through here, come out the other end, and on the other end of the resistor is one of our black cables that goes to a ground pin on this side. Now our other circuit, we're using the 5 volt pin on the Arduino here. That's where this red cable comes from. That's in the same row as one of the pins on the variable resistor. The power is going to flow through this. It will come out the other end, connected to the same row as the pin on the far end is the black one, and that goes to ground. And like the other sketches where we use the variable resistor, on the center pin in the same row on the breadboard, we have our signal wire, and that's going to A0 on the Arduino. And that's it. So next, we'll take a look at the code and we'll plug it in. I've got the Uno plugged in and everything's set. I've already uploaded my code to the Uno. I'm using a very slightly modified version of one of the examples. So the base examples under File Examples, AnaloginOutSerial. And I've just tweaked it a little bit. I define the constants the way I like. So our analog in pin A0 is the one where we're reading from the sensor pin on the variable resistor. Analog out pin, that's our PWM pin. Last output value, well, I'll show you what I'm using that for when we get further down. In setup, we're setting the serial output to 9600, which is the default that the serial monitor expects. If you set that to a value that's different from what the monitor expects, you'll probably get garbage characters coming through. The book does warn you about that, so you just need to make sure the two values match. Inside the loop, on every pass through the loop, we read the A0 pin to see what position we have our variable resistor set to. So that's always going to be our value between 0 and 123. Now we're using a new function that's built into the Arduino language. It's called map. And this one, you send it a value. You tell it the range of the value you're sending in. So we're telling it sensor value will be somewhere between 0 and 123. And what this will do is scale that raw value to a value that falls between this range. So we're saying take our values between 0 and 123 and scale it so it's a new value between 0 and 255. Because 0 and 255 is the range that the PWM pin expects. So it's just seems like a nice clean way to do that conversion. Okay, the next thing we do is write out to the PWM pin with our scaled value. And then down here, this is what I'm using the last output value for. What I'm saying is, if our output value on this pass to the loop is different from what it was last time, then write a new message out to the serial monitor. And then after that, we will update our last output value so it can check on the next pass to the loop. In the book, they mention again that it's good to have a delay inside the loop so you don't overwhelm the serial monitor with too much output. I think the number 2 is just an arbitrary value. You could make that bigger if you have to. It doesn't really matter. Okay, so I've already uploaded the code. I'll upload it again just so we can be sure. And there we go. So right now I have the knob on the variable resistor turned all the way to the right. And that should be giving it, oh, sorry, I forgot to open the serial monitor. I'll open that now. There we go. So nothing's changing here, so it's not getting any messages yet. But as soon as I turn this, we should start to get some. And if I turn it enough, we'll see the LED start to light up, and it will get brighter as I turn it more to the left. Okay, so the messages are coming through. I only turned it a little bit. So what we're seeing is the raw sensor value is 37, and that gets translated to a PWM value of 9. And I'll turn it a little bit more, and it gets brighter, and a little brighter. Oh. Now, this variable resistor is not the most sensitive piece of equipment, so every once in a while you'll turn it to a setting where it can't tell the difference between, in this case, it was flipping between 308 and 309 because it's just not sensitive enough. So I turn it a little bit more till it finds a nice stable setting. And I'm just going to turn it all the way to the left now. So now it's at its maximum value, 1023. That scales to an output value of 255. And you can see the LED is pretty bright. That's as bright as it's going to go. And now I'm going to turn it all the way down. And all the way up. And all the way down. So there's nothing else to see, but this is really a lot of great new stuff for us to have in our Arduino toolkit. We have a way to control input with a knob to turn things from a high value to a low value. I'm sure that's going to come in handy for a lot of different things. This debugging tool is just great. Being able to see what's going on inside the code in an extra window is going to be a real lifesaver, I think. I'm used to using software environments where we can write things out to log files, and I use that all the time during development to look for problems in my code. So without this, it's really shooting in the dark. So, what else have we learned? Yeah, I guess this is really just a sum up of all the bits we've done in this chapter and the other sketches. So, anyway, that's it. That's the end for chapter 7. This has been kind of a long one, but definitely a good one. And thanks for joining me, and come back for chapter 8.
As you